Hey everyone, thanks for being here today. My name is Himanshu Sharma and my teammates are Nabanita, Quasran and Rupam. We are excited to present about something called graph tool. If you ever worked with graphs or networks in Python, this is a library you will want to know about. Let's move to slides. Introduction to graph tool. So what is graph tool? Simply put, it's a super efficient Python library for working with graphs. Not bar charts, but actual networks with nodes and edges. The cool thing is it's built on C++. So while we use Python to interact with it, it runs really fast under the hood. That makes it perfect for working with big or complex networks. Significance in network science. Now, why does this matter? In network science, which studies things like social networks, biological systems, or even the network internet, we represent everything as a graph. Graph tool helps us dig into these networks to understand how they are structured and how they evolve over time. Key functionalities of graph tool. Graph tool can do a lot. You can create graphs from scratch, add or remove elements, and use layout algorithms to make them look nice. It has built-in tools for centrality, clustering, community detection, and even some heavy-duty statistical analysis. Plus, it supports parallel processing, which helps speed things up. Okay, installing Graph Tool. So, Graph Tool works best on Linux or Unix systems, and it does not run natively on Windows. If you are using Ubuntu, you can install it with a simple apt-get command. If you are on Windows, the easiest option is to use WSL with Conda. Okay. You can also use Google Colab for Graph Tool library. For this, you need to install Conda package manager on Colab and then install GraphTool module. You can follow these commands mentioned here. Okay, let's see some basic uses examples. Here is a basic example. We import the library, create a graph, and add a couple of vertices and edges between them, and then draw it. You can also apply layout algorithms like SFDP layout to make it more visually appealing. It's a pretty neat once you get the hang of it. Let's move to next slide. Graph analysis features. Graph tool isn't just about drawing pretty pictures. You can do actual analysis too, like finding the shortest path between two nodes, calculating page rank to find important nodes, or detecting communities using some advanced math. It's a super powerful for research or real world projects. Let's move to next slide. Visualization and layout options. When it comes to visualization, you have got options. Layout algorithms like SFDP layout, Fruchterman Rhine Gold layout helps arrange nodes in a way that makes sense. You can also export your graphs as PNGs, PDFs, or SVGs and customize how everything looks. Okay, let's move to next slide. Advantage of Graph Tool. So why use Graph Tool? It's a fast, like really fast, thanks to its C++ backend. It also has a ton of built-in tools that would take a lot of effort to code yourself. And for large or complex networks, it handles things much better than other Python libraries. Let's move to next slide. Limitations. Of course, nothing is perfect. GraphTool isn't the easiest to set up, especially on Windows. The community is smaller, so you might not find as many tutorials on Stack Overflow posts. And for beginners, the documentation can feel a bit intimidating. Okay, so let's move to next slide. Real world applications. Despite that, GraphTool has some amazing real world application. In social network, it can help find key influencers. In biology, it is used to map protein interactions. It can it's also useful in transportation, infrastructure, and even cybersecurity. basically anywhere complex networks are involved. Performance optimization tips. If you are working on a big project, here are some tips. Use graph tools, internal properties, maps instead of regular Python dictionaries. Take advantage of multiprocessing when you can. Save your graph in .gt format for faster loading later on. Okay, let's move to next slide. Comparison with other tools. You might be wondering how it compares to something like Network X. Well, GraphTool is way faster and has more built-in statistical features. But Network X is easier to install and better for beginners, especially if you are using Windows. Here are the some learning resources. If you want to dive deeper, the official documentation is actually pretty solid once you are used to it. There are also a GitHub repo with code and a bunch of tutorials and academic papers if you are looking for real world examples or advanced topics. Okay, let's summarize this. To wrap up things up, GraphTool is a super powerful library for analyzing graphs. It's fast, packed with features, and perfect for research or data heavy projects. Just make sure you are on Linux based systems and you will be good to go. Thanks a lot for listening. That's all from my presentation part. Now Nabanita will continue. So let's jump to the tutorial part. We will meet there.
Hello everyone, here we are gonna see how to install Graph tool into our collapse. So first we will start with installing Conda into our Google Colab. We will run the following code to do that. Then after installing the Conda Colab, we will import Conda Colab. We will run the following code to install the Conda. Once it is done, we will install graph tool into our code. So we will run the following code to install graph tool. It might take some time to install graph tool into our system. Yeah, the installation is taking place, you can see. It is taking little bit of time to install the graph tool. Yeah, it's going on. Okay, we are done with installing the graph tool. After that, do some we will get some networks from the graph tool library, and we will run a code and we will see how we can analyze the network there, the network data set. We will use the following code to do that. Here we are taking the following data set. Here we are using the data set of the cellular neuron. Then we will analyze its state using the following code. Once done, we can also draw the state also, so that we can see how the nodes and the edges clustered in the following data set. Okay, here you can see how it shows a colorful graph of the neural networks of the neurons of the brain. Next we are going to uh, next we can create empty graph, and we can initialize an empty graph using the following code. This will set up a blank graph with no nodes or edges. Next we can add two vertices. This will represent 2 points using our graph. So we are adding vertices v1 and v2. After that we can add an edge. So we can connect the two nodes using the following edge. Then we can visualize the graph structure using the simple visual representation of our graph. This will generate a simple visual representation of our graph. So here you can see that we have drawn a directed graph. Next we can draw directed and undirected graph also. So here you can see that I am trying to draw a directed graph. Here we are adding the vertices v0 and v1 and an edge e. Then we are drawing the graph using the following syntax. And then we will run the code, which is going to give us a directed graph. You can see an arrow. Next, if we make a change, that is directed equal to false, we can simply see that it is going to give us an undirected graph. Now we are going to add some properties into our graph, such as vertex color or edge weights, using the graph tools. So using that, we can using the following code we can add vertex color and edge weight. So for edge weight we are using this particular code. For vertex color we are using this particular code, and then we can add, we can give the edge weight for the following for the following edges, and we can give the edge color also. For v1 we are giving the following color, and for v2 we are giving the following color. The first one represents blue while the second one represents green. Then we can draw the graph. And we will run the code. So here we can see that the edge has a width of 25, that is it is going to be represented by some bigger line. We can also add multiple edges at once. So it's simply we can define the edges together in the following code using the labeled vertices. Here's how we can do. This particular code will automatically add vertices and edges in using the given labels. Next, we can visualize the graph as well using the following code. This will visualize the graph structure with vertices labeled by their particular indices. So here you can see how we can draw it. So after that we are going to add edges using the multiple weight of the edges. So as you can see here, we can add multiple edges at once in an unweighted graph using the following code. So here we are defining the graph where we are adding multiple edges at once. Then we can draw the graph and see whether we have done it properly or not. So here we can see the visualization. See, we have done different edge weights. Next, we can construct a graph using adjacency list as well. So given our adjacency list, we can construct a graph. So here we are defining the graph G. So you can see that we are defining the adjacency list. Using that we are defining our graph. Then we can draw the graph as well using the following code. So here you can see that we have drawn a directed graph, and it's very easy to draw using adjacency list. Next, we are going to use adjacency matrix to construct a graph. So in order to construct a graph using adjacency matrix, we have to import NumPy and SciPy.sparse. So we are going to do that so that we can define the adjacency matrix into our code. Now we are defining the adjacency matrix, and we are defining how sparse it is going to be. Then this is, we are defining the graph G, and the edge list will be our sparse M, and then we are going to draw the graph. And then we are going to run our code. So here you can see that we can simply draw the graph using the adjacency matrix. Next, we will see how we are going to construct a graph using the adjacency matrix, but we can add weights into that as well. So for that, from skypy.sparse, we have to import the new little matrix library. Then we have to import the array, which is going to be our adjacency matrix. And then we have to define our graph. So as you can see that we have defined our graph, which is going to be a directed graph. And then we are adding the edge weight. And then we are going to draw the graph. And then we are going to run our code to see how we can construct the graph using adjacency matrix, and we are having the weights added to it. Yeah, so you can see that the weights, some of the edges are in bigger in length, some are little smaller. From after this, Himanshu will explain.
Hello everyone, my name is Himanshu Sharma and I'm going to show how to add multiple edges in the graph. So there is a built-in function add edge list in the graph tool which can be used to add multiple edges in the graph. So firstly we'll initialize the graph and we'll call the add edge list method directly in which we pass list of edges. And now we call graph draw to show the graph. Okay. Hmm. So let's execute it. And as you can see, the graph has generated and it's a directed graph. By default, it generates directed graph. And here we have assigned each vertex index. So we can also label the vertices of a graph using strings. So let's see how can we do it. So it is also possible using the add edge list method. Okay. Hmm. Okay. So the same thing, we will initialize the graph, which will be directed, of course. Now we will create a array of names, of vertex names, basically. Now we will pass directly into the edge list, and we are passing the edges into the method, and for and also we need to add a argument hash equals to true, so that our edges can be converted into hash values. uh, Vertices can be converted, vertices names can be converted into hash value. So we need to create a property and named as v level, and here we will traverse each names of the array and will assign into the v level, and we'll pass into the sfdp layout, and now we can draw the graph. Hmm. Okay, let's execute it. Mm, mm. Okay, I need to. Okay. So here, as you can see, the graph has generated, and we have also labeled each vertex with the string. Okay, so in graph tool, we can also get the source and destination of an edge. So there is a direct method which is called the source and destination, which can be used to get the source destination of an edge. So let's see how can I find. Okay. So first let's initialize the graph. By default, it is directed, but we can also pass, and we'll add some vertex, and also we can add edges, and now we can print the source and destination of that edge. So here you and we will hold the uh, source and destination vertex. So first let's try it. Okay, as you can see that source is 0 and the destination is 1. See. Let's move to next topic, and hmm, in and out degree of a vertex. So we can also get the in and out degree of a directed graph, and there is a built-in function. So let's initialize a graph, and we'll create a graph adding some vertex, and we need to add a few edges also. So let's add first vertices. Now add edges. Okay, so let's draw the graph first. So let's print out degree and in degree of any vertex which we have defined. So let's calculate of V2 degree and in degree of vertex 2. Let's execute it. As you can see, the out degree of vertex 2 is 2 and in degree of vertex 2 is 1. Okay. We can also remove a vertex or a edge from the graph. So there is a built-in function given in the graph tool. So let's see. Mm, okay. Find edge. Hmm. So I can update this code. Hmm. Okay. So we can directly call remove edge method to remove an edge from the graph. Let me remove this. Now it's so here. Hmm. So as you can see, edge has been removed, and we can also remove the vertex from the graph. So let's call G. Okay, vertex. Mhm. So V1. Okay, we are removing V1. So let's execute it. And as you can see, vertex 1 has been removed from the graph. We can also calculate the local clustering and global clustering of a graph. And there is a built-in function in the graph tool. So first let's see how to calculate local clustering. Firstly, we will uh, access a data set named as karate. And for this graph, we'll calculate the local clustering. So we'll directly call the local clustering method and pass the graph G, and we can print. So here we will get the average clustering, average local clustering, and total local clustering. So let's execute it. So here we get the average and total local clustering. Same, we can calculate the global clustering of a graph. Okay, global clustering, compute. Okay, so we will access the karate data set and we'll print the global clustering. So in this we'll get two values. First will be average and the second will be a triangle ratio. Average triangle. Okay, here we get the values.
See how to calculate the different centralities in a graph. First, we will look at betweenness centrality. So, betweenness in a graph indicates how often a node lies on the shortest path of other nodes. So, first of all, we'll start by loading the graph from the data. So, the graph is loaded from the call blocks data, and after that, we'll calculating the betweenness. So betweenness is calculated and stored as a property. VP is the vertex betweenness and EP is the edge betweenness. So next we will draw the graph. So we'll use the betweenness to size the vertex and the thickness of the edges. VP is used to size the vertex and EP is used to define the width of the edges. So the vertex with higher betweenness will be larger in size, and similarly, edges with high betweenness will be thicker. So now we are plotting the graph. So now we can see that the vertices in the middle are thicker than the vertices in the periphery. Closeness centrality. Closeness of a node measures how close a node is to other nodes in the graph. So we'll start by loading the graph from the whole blocks data. Then we'll calculate the closeness. The closeness will be calculated and stored as a vertex property. And then we'll draw the graph and we'll use the vertex property to size the vertex so that vertex with higher closeness will be larger in size. So, so you can see we are using the property C to size the vertex and plotting the graph. Here we get the graph. Eigenvector centrality. The vector centrality of a node measures the node's influence by considering the importance of its connections, assigning higher scores to nodes connected to other influential nodes. So first we will load the graph from the call blocks data. Then we'll create an edge property W. So W is edge property. W is initialized randomly. W is used to assign weight to nodes. If not provided, all nodes will be given equal weights. So E is the eigenvalue and X is the eigenvector centrality. So now we will draw the graph. We will use the eigenvector centrality as previously to size the vertices. Plotting the graph. If page rank centrality. Page rank centrality is a type of eigenvector centrality. First, we'll load the graph from the Paul blocks data. Calculating page rank in graph tool is very easy. We just have to use the page rank function and pass the graph to it. Now we are drawing the graph. We will use the page rank to size the vertices. Finally, we have got our graph. We will look at degree centrality. So degree centrality is defined as the degree of a node divided by the uh, n minus 1, where n is the total number of vertices in the graph. So to demonstrate it, we will create a new graph and add vertices and edges to the graph. So we have added. So we've created a graph with 5 vertices and we have drawn edges from vertex 0 to 1 and another from vertex 1 to 2 and another edge from vertex 1 to 3. So, and an edge from vertex 3 to vertex 7. N is the number of vertices. Now we will calculate the degree centrality of each vertex. For that, we have created a vertex property and named it degree centrality. And then we are looping over all the vertices and calculate the degree centrality. So degree centrality will be degree of the node divided by n minus 1. So that's it. We've calculated degree centrality of all the nodes. Now we are printing it. So we will use vertex degree histogram to calculate the degree distribution of the graph. So, first we will create a random graph. Create a random graph using Poisson's distribution. And then we'll get the out degree for all the vertices and store it in histogram. And then we will plot it. The degree of the vertices will be on the x-axis and the frequency will be on the y-axis. Finally, we'll plot the histogram. Edge property histogram. We can use edge property histogram to calculate the distribution of edge properties in graph. So, we create a random graph. We've created a random graph G. We'll create an edge property with and we drop is an edge property, and then we will assign random values to the edges. Okay. So now eprop has random values. So now we need to find the distribution of the values of eprop. For that we can use edge histogram function. Using gt.edges, we can get the distribution of the values of eprop. Now we will plot it. Edge weights will be on the x-axis and the frequency will be on the y-axis. Distance histogram. Distance histogram is used to calculate the distribution of shortest distance path in graph. To demonstrate it, first we will create a random graph. We have created a random graph. Now, the graph tool provides a simple function to calculate the distance histogram. We just do gt.distance histogram to get the distribution of the shortest path distances, and then we will plot it. We will label the x-axis as shortest path length and y-axis is frequency. Plotting. Finally, plotting it, we get the graph.
Hi, I'm Rupam Roy. So we will generate a graph G. We will create an empty directed graph G on which we will compute DFS and BFS later. Our graph will have 10 nodes as string leveled. This is how we can add nodes in a graph. String leveled using for loop. And we will add some custom edges in the graph. The edges are 0 to 1, 0 to 2. We will add edges using add edge method using for loop. And the visualization part, we will make a function that will visualize the graph. and call the function. Let's run it. Hope everything is fine. This thing's enough. Let's run it. Okay, so it's good. So let's do the BFS part. So we will create a class for this. The class will have a constructor and two methods: discover vertex, examine edge. Now perform BFS from vertex 0. And this part will print the BFS tree information. And visualize the BFS tree. Correct the indentations. Run. And yeah, it's the BFS code, and this is the BFS tree. Now let's do the DFS part. DFS, DFS on. We will do same as BFS here. A class that will have a constructor And one method that is discover vertex. Another and another class method examine age. And another class method Phoenix vertex. And start DFS from vertex 0. Print DFS tree information here. And last part to visualize the DFS tree. Correct the indentations. Yep. And this is the DFS tree and information. This is the code. Hello guys. So we will conclude our tutorial on a simple hands-on on a real data set. We will take this data set. Uh, you can visit this data set from here and you can download this, the zip file. So first we need to import the libraries. Like, of course, we need graph tool and we also need matplotlib pyplot and matplotlib cml along with numpy. Now input the dataset print average vertex and print average age. Run it. Is average vertex and average edges. Now we will compute the between centrality of the opposite dataset. So computing between centrality is kind of a pretty straightforward approach. Right? And now we are going to visualize the graph. And the graph is so this is the graph of the between centrality. Pretty messy. So now we are going to compute closeness centrality, and closeness centrality is also as straightforward as betweenness centrality. And it is quite easy. It's three lines of code, and we are visualizing the closeness centrality graph. Right, that's all. And let's run it. And this is the graph about closeness centrality. Now let's compute the degree centrality. For this, we need degree property map. Okay. Take the largest component first, filter out the largest component. Now, degree property map, total stability. And visualize the graph of degree centrality. Let's run it. This is the graph for degree centrality. Finally, we are going to compute the degree distribution histogram. By array. You could go there. And visualize the pie plot. And this is the histogram of the